Thank you. As I told you that this so-called transistor, MOS transistor switches or pass transistors or transmission gate, there are three names for it. They can be used intelligently to realize different combinational logics in a very compact form. There are relative merits and demerits. So I will discuss today how the various combinational logics can be realized using the pass transistors. Okay. Let us see some very simple form. Suppose I want to realize a function which is f is equal to x plus, say, y bar z. Okay? What I do, I can realize this, as you know, that as already very much well known to you, that connecting switches in parallel is equivalent to OR function, whereas in series is equivalent to AND function. So you do that. What you do, you take a switch here and connect X, then you take two switches in series, and in one you connect Y complement, the other you connect Z. Then at one end you connect 1. That way you keep it high. One end you keep it high. Then at the other end you are expected to get the function f, which is equal to x plus y bar z. So what I have done, because this is x or y bar and z, x or y bar and z. So what I have done, I have taken a switch which is nothing but a transistor nMOS switch. I have assumed, but it could be a CMOS switch also, whatever I have discussed at the end. nMOS switch suffers from that limitation already discussed, the voltage degradation, but otherwise you can use CMOS switches also. nMOS is simpler. nMOS switches are much simpler. So this is a diffusion, and then I have a poly. That means there is a MOSFET here underneath, and you are connecting your X input here. And then there is a long diffusion. There are two polys, means two switches in series, two transistors in series. At the input of one transistor you have connected Y bar, Y complement, and at the other input Z. So if you ignore this part, if you ignore this part, it is nothing but Y bar Z and function. And when you OR it with it, then it becomes X or Y bar Z. Okay? And you get at this output side, it can be easily verified. For example, when X is 1, and whatever may be the Y and Z, you can easily find that F will be always equal to 1. Because when this switch is on, 1 will be transmitted, whatever may be the state of these two switches. On or off does not matter. Similarly, you can verify all these things. This is a standard description, you know, that the simplest, most primitive level discussion on the AND or OR gates. You know that connecting switches in series means AND operation, in parallel means OR operation. Exactly that I have done. But what is the drawback of this combination? What is the drawback of this combination? Suppose when X is 0, and then Y is 1 and Z is 0. Anything, 1 or 0 does not matter. 1 or 0. Then what is going to happen to the output? What is your expectation? F should be 0. Okay? F should be 0. But can it happen here? Or will it be very reliable? This particular other thing, when F becomes 1 is okay, no problem. For any combination of X, Y, Z, when F is 1, no, there is no problem. But when for any combination which makes F is equal to 0, Do you realize, do you apprehend some problem? Suppose at the last state, just immediately before this, f was 1. And as soon as you make x0, y1 and z1 or 0, this becomes electrically as this is off. And you know this MOS logic, that 1 will be retained. So you will not get 0 here. You have to allow some path for discharge. Am I correct? So this will be uncertain. So if you want to realize a pass transistor logic very simplistically like this, it is not possible because it will not function properly. There will be a lot of malfunctioning. So how to, is there any way out? Can you solve this problem? I want that whenever f becomes 0, there should be a path for discharge. According to this functional description, for any combination of x, y, z, if s is to be 0, at that instant, there should be also a path for discharge to 0. How can you provide that? Yeah, you can place the dual of this, that is complement of this function f. Make a configuration here, and at the input you keep 0. Let us see how is it possible. So what you can simply do is, what is f bar? F complement is simply equal to x and y plus z bar. X bar, yes, definitely. X bar and y or z bar. Okay? Then you just configure it like this now. So now, this is your x as before, this is your y bar as before, this is your z. Now we have got x bar here, y here, and z bar here, and this is 1, this is 0. So you get at f, which is simply equal to x plus y bar z. In this case, you can easily verify that when f is 0 for a combination of this, this path, because this is a dual of this, will complement of this, will provide a short circuit. So this node will be always discharged. There will be no problem. You can easily verify it. But any combination of x, y, and z, whenever output f is 0, this combination provides a short circuit path. So the output node will be automatically discharged. So even if at the earlier stage, during the earlier clock cycle, f was 1, there will be no problem. Automatically the 1 will be pulled down to 0. But unfortunately, we have to use larger number of transistors. But anyway, if you compare this x plus y bar z, this function, if you want to realize using standard logic, standard static logic, how many transistors will be needed here? How many transistors will be needed here? You see that I have to make double inversion, because there is no complement here. Either you produce the complement of that, do you follow? You can rewrite the whole thing in a different way so that you get in invert form, or you have to use for this how many transistors? The invert of this, if I want to AND or invert, 4, and then another inversion 2, so 6. And how many I have used? 3. So, and one can see that you will find here how many transistors I have used? 6 transistors. 6 transistors. So one can see that ultimately there is not much benefit to be derived if you do this so far as packing density is concerned. But one great advantage of this is, in this case, you don't have to maintain the ratios, because these are all independent switches. The ratioed design is not important here. These are all independent switches. You don't have to maintain the ratios. You want to just transfer ones and zeros. And we shall also see that there are two kinds of logic. One is called ordinary full custom type of logic. The other is called structured logic. Structured logic means it is developed in such a way that there is a regular structure available on the IC. And that regular structure is somehow configured in such a way that any logic function can be implemented in a very easy manner. So that the design is very simple. As well as, that is what is called structure. For example, I think you've heard of gate arrays and other things. These are all structured logic. There is already a structure available. Only thing is, you have to interconnect in such a way that any logic function can be realized very easily. You can see that this particular approach of pass transistor logic can be considered as a structured logic if I draw the corresponding stick diagrams now. This stick diagram is, that what is the difficulty of this stick diagram? You are showing all inputs at different points and all these things. We have to, that all the inputs are to connected at one end, and output in one side, and maybe power supply and ground 200 points. Okay, but here I have drawn in such a way. What I have to do, therefore, I have to extend this thing, and so on. Actually, if I want to connect all X, Y, Z, etc. at one side, I have to bring all these poly connections at one end, and exactly that is done. And what is actually done to make it more symmetric, more structural, is as follows. For example, let me draw. Suppose 4, 1, 2, 3, 4 diffusion lines, okay? And this is 1, this is 0, and then what I do, I just put a number of polylines, parallel polylines like this. A number of parallel polylines, but I draw it like this. Because here I have some problem of drawing it, but till I will do you. Just see what I have done. I have connected, this is my, or rather, let us see it like this. I have to connect X in one branch, and that I have put, so this is an X, this is the polyline which transmits X, which carries the signal X. And these blocks are drawn to, so that, that is why, that is the limitation of the stick diagram approach. I said that whenever stick diagram, poly intersects diffusion, there is a transistor. But suppose I want in some situation that when at this contact, at this crossover point, there is no such transistor. It may happen because poly is one level and diffusion is another level. This is separated by an oxide. It is not always necessary that whenever there is a cross of poly and diffusion, there should be a transistor underneath. But why we do it like this? Because if you remember the transistor structure, MOSFET structure, you know that both source and drains are diffusion, and gate is just something in between, isn't it? Between one source and the next drain. So we can say it like whenever there is a poly crossing a diffusion, structurally, there is a transistor. Actually, transistor configuration is like this, but there may be many situations when I do not need this transistor. So to avoid that problem, what I have done, I have put these boxes. These boxes, you see that I have made a discontinuity of the poly line. It is like this. So the poly line has not crossed over the diffusion, and that means at these 3 points there is no transistor. The poly and diffusion are isolated. Only at this point there is a transistor. Okay. Thereafter, I told you that always at the input I have got some inverters to produce both the function x and x bar. So automatically at this point x bar will be produced and x complement will be produced. Now what is needed in this circuit? I need that x bar is to be applied at a 0. The diffusion lines carrying 0, and it is in series with this parallel combination. So what I can do, because you see that here in the 0, I use 4 lines, 4 diffusion lines. So what I will do, I will put a transistor here and here both, so that it is equivalently 1 transistor on this single line. Okay? Whereas I will not put any transistor here. So what I will do is simply this. You could say that why unnecessarily extend the polyline? That could be done, but for structural symmetry, you know that design becomes very simple if you just make a very symmetric kind of matrix structure. That is what I have done. You see that this is x bar, this is x complement. So here there is a transistor, here there is a transistor, as indicated here. Here there is on a single line, but if I put on both lines, it is equivalent to single transistor. So here there is a transistor, here there is a transistor. So I have applied my x complement signal at this 0 line in both branches. So equivalently it is on a single branch. But here there is no transistor. Similarly, let me go for y. So far as y bar is concerned, you see that for y is concerned, there is 1 transistor here. No other y. So what I have to do simply for y, I have to isolate this one, and also this one, and I put this. This is y. Am I correct? Then let us consider y complement. Y complement, you see that in this branch, there is no, it has been applied only to this branch, not in both lines. So what I have to do, I have to put isolation here only for showing. That is the advantage. You see that this isolation I am showing simply for drawing the stick diagram. Otherwise, whenever I fabricate, it is very simple. You just allow another line straightforward passing, no problem. Sorry, I think I have just drawn it oppositely. It should be in the other branch. Oh, sorry. This is not there. This will be there. This is not there. Wrongly I have done. So it should be a continuous line. For Y, similarly for Z, for Z you see that there is only one here. So what I do, I isolate this, I isolate this, I isolate also this. This is my Z, and again for Z complement, you see that it is on this line. So on this line, somewhere here. So I will put just this one. Other things have to be isolated. Am I correct? Oh, this is Z bar. Sorry. It is on this line. So this is the situation. So I combining them, ultimately we get here F. So what is the advantage of this diagram? What is the special merit of this diagram, the drawing it in this fashion rather than in this fashion? Can anyone please tell me? If you compare this one with this one, what is the merit of the second? It is structurally symmetric. There is a matrix. Only things, in certain locations we put the transistor, and in certain other locations we do not put the transistors. Exactly this we do when you develop a ROM, we shall be discussing afterward, programmable ROM, mass programmable ROM. There are certain ROMs which is manufactured. If you give your program, if you give your memory requirement, or rather program to the manufacturer, they will make it for you, but it will be a permanent ROM. You cannot change it. This is normally done for application where some millions or at least thousands of such chips will be required. Whereas, as you know, today there are variations, field programmable, etc. is coming. I shall discuss that afterward. So that is what is known as structured logic. Now, what is the basic drawback of this particular structured logic? If you have understood technology a little bit earlier, in my earlier discussion, can you again, any one of you tell me that what may be the problem in this particular implementation? You just see that I have four long, this is example is for a very small function. In actual practice, the function will be quite large. And you may be required to produce 6 or 8 output functions, F1, F2, F3, F8, from 16 input variables, A, B, C, etc. Or 8 input variables. Let us consider 8 input variables, A, B, C, D, etc., and 8 output functions. So what will be necessary? How many diffusion rows will be there in that case? Per function 4, there will be 32. And for input, how many poly lines will be there? 16. 8 input bin or 16 input, it will again be 32. Okay? So you see that all your input signal is being applied at one end, and the signal is being transmitted by poly line. For the fast diffusion line, the signal transmission, there is no problem because the fast diffusion line is very near. The RC delay will not be that much. But what about the last line on the other end of the chip? Because polysilicon, after all, has got much higher resistivity. It is heavily doped. The polysilicon gate which is used for MOS realization is heavily doped, N+ usually. But its sheet resistance is usually quite large compared to metal sheet resistance. Suppose if I had used metal gate, the sheet resistance would have been very less. So RC delay for metal gate would be very small. But because you are using a level as poly level that is normally used also, because we have to use at least two to three levels of metallization. So one level is always poly level. Please remember. So what is the problem here? Yeah, there will be unnecessary signal delay and there will be delay inequalization. Delay here and delay here will be different. So ultimately there may be problems if this is an asynchronous logic. But even in synchronous logic, you have to use it at a much lower clock frequency. You have to wait sufficiently so that the thing stabilize. Okay? So this is the problem if you use all the inputs, like, because you see that here the poly lines will travel from one end of the chip to the other end of the chip. So this is a drawback. Can you suggest something to get rid of it? And that is as follows. Naturally, the solution, as expected by all of you, that replace all these poly lines by metal lines and use local poly lines. Is it all right? Replace all the poly lines by metal lines. That means all the columns, instead of being poly, is now metal, but use local poly lines to realize the transistors wherever needed. So you get the second realization, and that is as follows. So these are all metal lines, double lines. But you'll have to sacrifice more space for this. Automatically it becomes x complement y z. You see that here I have plainly 6 metal lines all through passing, and these are all on oxide, so they are it is electrically isolated from the diffusion or poly, whatever the levels may be there underneath. Only at local points, for example, I want a transistor here, so I have a cross cut and a small short poly line. and I have formed the transistor. There is no such transistor here. Similarly, I have done exactly the same thing as other location. This thing is done in ROM also, you'll find afterward. Exactly the same thing is done for MOS ROMs, called mass programmable read-only memory circuits. Exactly similar thing is done. Entirely a structured logic. Realization is rather simple. What you have to do, it is called personalization of the array. You have formed an array of rows of horizontal rows, means here rows of diffusions and columns of metal lines, and then at appropriate locations you have cross cuts called via holes, small vias, and have short poly. That means here, of course, you have to, the mask should contain. Another thing is normally done, you know that what is usually done, I have at each intersection below this there is a transistor. When I will actually develop the chip, what I will be doing, I will just arrange a matrix of MOSFETs. These MOSFETs will be all located below, but they are not connected. Only those which are useful, you connect them. That means you have to have a personalization only in the which level? Metal via hole etching and poly level. Because you have to somehow etch at certain location. What I have to do in this case, actually poly level is below this. Please remember, metal comes at the end. Actual VLSI realization, metal comes at the end. Metal deposition and patterning comes at the end. Before that, poly comes. So what I have to do? Already I have everywhere MOSFETs. Everywhere MOSFET. At all point, intersection point underneath there is a MOSFET. But these MOSFETs are all covered by oxide. They are not accessible. Even there are polylines also. So at each intersection there is a polyline. At each intersection there is a polyline. Okay, already the polylines are available. But then what I do, while after the transistor fabrication and polygate fabrication, so please remember I am repeating, I have a MOSFET at every such intersection, at node points, at every such intersection point. I have already every point there is a polyline like this, local short polylines like this. Then I cover it by an oxide. Then etch windows in that oxide only in these locations. And certain other, naturally, that while this is important. Before metallization, I have to etch windows for all these via holes as well as all these electrodes for the terminals, according to the layout of the IC. And then you etch metal line, and automatically it will be like this. So you just see, in this case, you can pre-process the wafer earlier. There is no need to start to design from the very beginning and have a dedicated chip called full custom IC. There is no need. This is called a semi-custom IC approach. We shall discuss this thing in more detail afterward. A semi-custom design or a semi-custom IC approach. What is done is already the array is available. Even the chips are also fabricated. Up to what level? Just up to the stage before metallization. Up to the stage before metallization, chips are already fabricated. All the big wafer, not chips, wafers are fabricated. These are called master slices. Such prefabricated wafers are called master slices. Already is available. Then according to a demand, now you tell the company that I need this. What you will do? You will sit down with this computer and design two things. A mask for these contact holes and a mask for nothing, because so far as metal is concerned, it is already done. Only input output, because bonding etc. has to be done, so you may not need all the inputs etc. So that kind of information is necessary for you. Otherwise metal limbs are also, that is a very simple thing. Metal lines are already there. The standard masks are available where metal lines are there. These are just rows, columns. Only thing is needed, holes. That's all. So that way, this is a very, very simplistic kind of approach, but what is the major drawback of this? If it is a very large IC, suppose if I want to have, as I was giving, a 16-bit kind of thing and at least 16 output functions. Normally, number of output functions, there is no problem, but if the number of bits is too large, then can you envisage what is the problem you are? Same voltage degradation for using NMOS logic. Whatever I have discussed is NMOS logic. The voltage degradation problem will be there. So you have to suitably adjust the areas of the transistors, and all these problems are there. And therefore, this is good only for a reasonably not so-called today's VLSI. When we are thinking of millions of transistors, this approach is not that very good. So it was an intermediate phase. Let me tell you very frankly, this pass transistor logic is very rarely used today. It was an intermediate phase. It is very simple. In your laboratories, in our laboratory also, it can be developed with less difficulty. It's not a very difficult job. And for simplistic kind of requirements, as I said, even 8-bit, there will be not much problem. It can be realized. But whenever you go for a logic circuit, what is your actual approach? I think you have studied that in your pulse and digital circuits. A function, a combinational logic function, can be expressed in a way, as you know, that in the term, in a very crude, big form, in a large form. Always you try to minimize it. Canonic, yeah. So you have to minimize it, and that approach is always. So what can be done? In fact, in the case of pass transistor logic, Shannon's theorem can be applied to minimize logic. We can see a very simple example of it. For the same thing, how it can be minimized, we can see a very simple example of that. Or rather, let me introduce that. You can try it yourself. Okay? Suppose the same function f is equal to x plus y bar z. I want to reduce, at least rewrite in a different other form, so that ultimately size is reduced. That the number of transistors is less. So you apply, say, so-called Fannin's theorem. So you know, according to this, if can be written as x1 into f1 of 1 x2 xn plus x1 complement of f1, sorry, not question of f1, f0 x2 x3. So f is a function of n variables, x1, x2, xn. It can be written as x1 into f of, instead of x1 it is 1, always fixed at, clamped at 1, and then x2 to xn. Similarly, x1 complement into f of, instead of 1 it is 0, x1 is clamped at 0, then x2, x3, xn, etc. And using this very simple thing, you can rewrite f in this fashion. Suppose we assume y bar z as our x1 and this x is x2. So what is the form becoming? Y bar z is our x1 and x is x2. Then what will be the form becoming? Y bar z into f1, that means 1, plus what? Complement of this, and then x. So it becomes simply y plus z bar into x. because this is 0 in it. Just apply this Shannon's theorem and this becomes. What I have done simply for y bar z, I have assumed this is x1 and x have been considered to be x2. It is a function of two variables where x1 is y bar z and x2 is x. So you can rewrite like this. And if you can do so, then you can finally represent the same logic in a little bit simplistic manner like this. But anyway, this representation there is not that much structured. This is more custom design type rather than semi-custom design type. I don't have time. You just see exactly what I have done. For realizing this one, I have used this. Whereas for realizing this, I have used this. And automatically, the discharge problem is not there. But anyway, this kind of approach is not that much universal. So naturally, you have to sacrifice the design cost. Design, in this case, design cost will be much more than in the last case. But anyway, chip area will be very small, power dissipation will be very less, and speed will be more. Therefore, you see that the pass transistor logic is a very good concept. It can be used for realizing combinational logic in a very simple fashion, in a very low cost fashion also. But ultimately, when the size of the chip is larger, when the many variables have to be handled, then it becomes difficult simply because of the, otherwise you can use CMOS gates. But CMOS gates technologically is a more jam. It is used in combination of with normal inverter. We shall be coming to that after. Just pure pass transistor logic today has got very limited application simply because of the development in other phases. For example, CMOS has come in a very useful logic which is called Domino CMOS. I think you've heard of Domino CMOS. We shall be discussing that afterward. Most of the CMOS logic, whatever is realized today, this is Precharged CMOS logic and uses domino concept. I think today, let me finish here. And in the next class means on Tuesday, we are planning to. I was thinking of taking a class. Let me forget about taking class. So I will just take a class test on Tuesday. And that can be held, that may be held either here or in our classroom. What is the classroom? Yes?